What happens to an SQL query from the moment it enters the system until you get the results back? How does the engine check for things like syntax errors and so on? What kind of information does the engine need in order to produce an efficient query plan? These are all very important questions, and we're going to answer them and more in this video. Hello and welcome. My name is Elhelw, and today we are going to talk about SQL. We've already had a couple of videos talking about relational databases. We've talked about storage, we've talked about indexes, and we've also talked about relational algebra and how it is the basis for the SQL language that most of us are familiar with. SQL is pretty much used in all of the relational database management systems. It is classified as a non-procedural, or another word for that is declarative language, which means that you only specify what you're looking for, but you don't tell the system how to get it. This is very different from relational algebra. In relational algebra, as we've seen, it is a procedural language because you specify the order of the operations that you execute. In SQL, you specify just kind of like, again, what you need from the query, and then it is the job of the query engine to come up with the plan or how to execute that query. So today we're going to be talking about the life cycle of a SQL query. There will be different modules in the query engine that we're going to talk about today. We're not going to get into deep details for each one of them. We will have separate videos to go into the deep dives into some of these modules, but today we're going to give an overview of what these components are and what happens to the query from one of these modules to the next. So to start off, SQL queries or SQL statements, or pretty much any database system or anything that has to do with data, there are four basic types of operations. They're usually referred to as CRUD operations as an acronym. So the four basic types are creation or insertion of data. This is where you add new data to the system. Reading, this is where you retrieve the data. Update, this is where you update, change the data, and then delete is where you destroy data. So these are the four potential operations in any data management system. In SQL, those are mapped to insert statements, select statements, update statements, and delete statements. We're going to focus on the select queries specifically. Select queries are way more common than any of the others because usually you write the data once, but you read it multiple times. Also, it is the most complex because it allows for more things that you can do. You can do subqueries, you can do very complicated conditions, you can do sorting, you can do aggregation, all of these things that are not part of, let's say, insert or updates. So select statements are the most complex and the most common. And they're often also part of update or insert statements. So this is what we're going to focus on today and see how the system handles those. So basically we have something called the query engine. At a very, very, very high level, most people think of the query engine as a black box, this mysterious thing where you put a SQL query from one side, get the results from the other side. Most people don't really know what happens inside of that. Most people don't want to know what happens inside of that because it's very complex, or kind of like, some people think it's scary. But today we're going to try to break down that myth and see what actually happens inside that. So let's zoom in into the query engine and see what happens there. Starting from the beginning, we start with an SQL query, something like this. Could be any query, big or small. Some queries can be huge, can have 300 or 3,000 tables and different number of joins and complex operations. Other queries might be very simple like this one. So what happens there? First thing to note, this SQL query or any SQL query, when you look at it at a very low level, it's just a string. It's a sequence of characters. The system cannot deal with that right off the bat. So we need to be able to transform this to something that has more structure and more meaning to the query engine. So the first component that does this is the parser. So the parser's job is to take that string and convert it to something else that we can deal with it later on. So let's have an example. Again, this is the query that we're dealing with here. Again, this is just a sequence of characters. It doesn't mean anything to the engine at this point. We want to be able to convert this, instead of just like some characters one after the other, we want to convert this into some tokens. Tokens are things that have more meanings attached to them, things that the system can interact with. What are these tokens, or what types of tokens are there? Some of the token types are keywords. Keywords are basically things that are part of the SQL language itself. Things like select, from, where, and, or, null, group. All these are keywords or parts of the language. There are other things like, operations, like, greater than, less than, equals, arithmetic operations, plus, minus, all these things. So these are symbols that have meaning to the system. There are other symbols aside from operations, things like, parentheses, quotation marks, dot, comma, all these symbols. They also, have some meaning depending on the context in which they're found. There are constant values. So in this particular example, when we have status equals active between quotes, so that active within quotes, this is a string constant. When you say age greater than 20, this 20 is an integer or a numeric constant. So all these are constant values. The system should be able to recognize these and then kind of like, deal with them in the appropriate way. Anything aside from all of these is referred to as an identifier. So identifier is basically like a word or like a sequence of letters and numbers that does not belong to any of these categories, and the system will assume that this might be a name of something, a name of a variable or a name of a table or column or whatever it is that's not part of the language itself, but something that we can refer to. With that in mind, the parser works as follows. Again, this is kind of like a very basic explanation of how it works. There are more details that we're not going to get into today. But at a very high level, the parser just kind of like, does a pass over the query text, letter by letter or character by character, and tries to match whatever it has found to one of these, token types that it has. So it will, go over the query, and as it does that, it starts, creating these tokens. So we're going to have a select token, because select is a keyword, followed by an identifier token called name, because it doesn't know what name is, so it says this might be the name of something. There's a comma, there's a phone identifier, again this might be a name of a table or column or whatever it is. There's the from keyword, there's the user identifier, the where keyword, and so on and so forth. There are some operations in the mix, like we have the equals, we have the greater than, there are some string constants there as well. So now we have converted the whole string into a sequence of tokens. Note that at this point, we're not doing any validation on the identifiers. Like, it doesn't know that user, like, is that a table? Is that a column? What is that exactly? Does that even exist or not? It doesn't know. It doesn't care. The parser job is to just convert the string into that sequence of tokens. There are some validations that it does, but validations like what? Like, one of the things, for example, it can do as it's parsing, let's say it finds this, open code, right? It knows that whenever it finds this usually means that there is a string constant. So it needs just to find the matching one, and then whatever is in between that is going to be the string constant. But let's say we forgot to add that. We forgot to close the string. So basically it found the first one, and it's parsing, it's expecting to find the second one, but it reaches the end of the string and it has not found the second one. So then it will know that, okay, there's something wrong here. You are missing the closing code. So this is a syntax error right there. Another type of errors has to do with the query structure. It knows that, for example, the query must have a select, must have a from, it may have a where clause. So if it parses the query and let's say it doesn't find the from clause, it will tell you like, hey, this query is missing the from clause. So there's a syntax error here as well. Some systems allow you to write a query without a from clause, but let's say if it was required, then this one will complain that it cannot find it. So again, these are the kind of checks that can be done while parsing the query. Again, it has nothing to do with the meaning of phone or name or status or these things. It doesn't understand those. So it assumes that these will refer to something. So based on that, this is okay. Once it has finished this parsing and got all the tokens and there's no syntax errors, it takes this parse tree and it takes that kind of like sequence of tokens and creates a parse tree. So a parse tree is basically just trying to have a tree that represents the query, the different parts of the query. So again, we're adding more meaning to what we have so far. So now we're going to have this tree. We have the select clause, we have the from clause, we have the where clause. So in the select clause, we have all the identifiers, and because they are in the select clause, then it assumes that these are attributes. Anything in the from clause, it assumes that this is going to be a table. Again, it doesn't know if that's the case or not. It just says because this is under the from, then it should be a table. And then we have the where clause with all the conditions and all that. It puts them into a tree shape, and again assumes that things like status and age, since those are identifiers, assumes these are columns as well, and then the others are constants. So far, this is a parse tree, and this looks correct from the parser's point of view. There is no checks on, again, like the tables and the columns and anything like that yet. If the query has things like order by, group by, these will also be part of the tree. Also, this tree, that it doesn't have like a standard structure. Like the structure of this parse tree might be different in Postgres than what you have in MySQL, and so on. So each parser might be different in what it produces. So going back to our diagram, now the parser outputs a parse tree. What happens with that? What's next? Next, we go into another module that does the validation that we're missing, the validation on the columns, on the tables, and all that. This is the query analysis module, or the analyzer. So this analyzer performs something that we call semantics checks. So the parser was doing like syntax checks. Now we're doing semantics checks. Semantics meaning look at the things mentioned in the query, check, for example, that all the things that we assumed are tables, check that these are actually tables and they exist. Everything that we assume to be attributes, check that these are actually attributes and they exist in the tables that we have. Make sure there is no ambiguous references. For example, if the query has multiple tables and all of these tables, each of them has a column called ID, and we're referring to the column ID in the query, then we don't know which one. Make sure that if there is such a thing, that we have a prefix or something that says ID that's coming from table T or something like that. It checks that if we have any function calls in the query, that these functions are defined somewhere and that the function definition matches the call site in the query. It also checks for types. So whenever we have things like a comparison, like when we say where status equals active string, it checks that the type of that status field is something that we can compare to a string. Or if we're comparing something to a date, then it checks that this is something that we can compare to a date. So, it makes all these checks as well. So looking at the parse tree that we have, first thing is going to look at that table user. Yes, that table does exist, so that's good. It's going to look at the select clause. Okay, so attributes, name, and phone, they do exist. They are part of the table user. So again, we're good here. Now look at the where clause. There is a attribute called status in the user table, so that's good. And then it does the type check. So the type of the attribute status, of the status attribute, let's say, is a string, so it can be compared with that constant, so that is also valid. And then it's going to go to the age attribute, but it's going to say, no, actually, I do not have an attribute with that name. If we look closely, we'll see that I actually mistyped age. I put AGEE. So it will says, no, that nothing with that name exists. So if I look at the table definition, I'll find, oh, actually, yeah, it has just one E. So that's one error that the analyzer will give me. So if I correct this mistake, then it will pass. So let's say I corrected a type age correctly. Now we have the parse tree, everything has been checked, all the types have been validated, everything is good. Then the analyzer will start creating a query plan. Query plan is basically the relational algebra equivalent of this query. Remember when we talked about relational algebra, there was things like selections, projections, all these operations. So we're going to now put these operations in the order corresponding to the query. So in this query, we have one table user. We're going to filter it based on that where clause, and then we're going to project only the attributes name and phone. So it's going to look like this: table scan on user, followed by a filter with the conditions that we have, followed by a project on name and phone. And remember that we read these plans from the bottom up. So it starts at the leaf level. Once that is done, we execute the filter, and then we execute the project in that case. So this will be the initial query plan. Theoretically speaking, we could take this, execute it, and we will get the result and we would be done. However, this may not be the best plan, so that's why there's more work to do. As we have seen, the analyzer takes the parse tree and then produces that initial query plan. In many systems, or in some of the documentation or some of the literature that you might read, some of them, they combine the parser and the analyzer into one component. So you might see just a single component called, parsing and analysis, or just sometimes they just refer to all of this as parser that takes the SQL statement and produces that initial query plan. So just in case you see this somewhere, this is a possibility. Okay, so one question. We mentioned that in the analyzer, it does this validation, right? About the tables, about the columns, about the types. How does it know? How does it find this information? Where is that information found? Every database system usually has this component called the catalog. The catalog is a collection of metadata. Metadata about the tables, about the attributes, about indexes, about types, about all of that. This data, pretty much, this is maintained by the database. It's usually, in many systems, it's stored also as a set of tables, like system tables. These are defined and maintained by the system. Every time, let's say you create a new table, then it updates the catalog with the information of that new table. If you update the table, add new column, remove a column, it updates the catalog automatically. When you create an index, it updates that in the catalog. So that catalog basically is a collection of all the objects that exist in the system, their names, their types, how they relate to each other, and all that. So the analyzer just looks at the catalog and figures out if a table that you mentioned in the query exists or not, if a column that you mentioned in the query belongs to that table or not, what's the type of that column, all that from the catalog. All right, let's see what the catalog looks like in Postgres. So I've created this sample table called foo. It has 4 attributes: integer, varchar, date, and double. First one is also a not null, the A attribute, and it's also the primary key of that table. Let's check out how many tuples are there. So if I do select count star, then it'll give us a 1024 rows in that table. Now, the catalog has multiple tables in Postgres. One of the most important tables is called pg_class. So let me describe the table just to see what information is there. So this has all the information about the tables and other objects in the database. So for each table, it has an OID, which is like the ID of the table. That's a system ID. The relation name, so the name of the table. The relation namespace, we're going to talk about this in a bit. Type, because it covers tables and views and indexes and other stuff, but let's just focus on tables for now. The owner of that table, the number of pages, the number of tuples in that table. So yeah, there's a lot of information about the table level. What it does not show the attributes of that table. Those are found in a different spot. So we'll come back to that later. But let's see first of all, what information can we get about that table foo that we have? What can we see in the catalog? So for example, I'm not going to list everything because it might be too hard to read. But let's, for example, list the OID, the relation name, the pages, and the tuples. So I'm going to select OID, rel name, rel pages, rel tuples from PG class where rel name equals foo. This is the table that we have. So yeah, that will give us this information. So this is the OID of that relation. This is the name, which we already know. The data is stored in 7 pages, and we have a total of 1024 tuples. So this information is maintained in the catalog, and the query engine has access to it. Now, where are the attributes? So the attributes are stored in a different catalog table called PG attribute. So again, let's look at that table and what it looks like. So it has, for each attribute, it lists the relation ID, where that attribute belongs, the attribute name, the ID of the type of the data in that attribute. We'll see that in a bit. The length of the data in the attribute, the number of the attributes. So like, the order of the attribute in the table. Is it the first, second, third, fourth, etc.? And then other information there. For example, whether the attribute is designated as not null or not. Yeah, so there's a lot more information in there. Again, let's see what this data will look like. So I want to get some information about the attributes from table foo. How do I do this query? I'm going to do a subquery here. So the subquery says select OID from PG class where rel name equals to foo. So I'm getting the OID of that relation. And then I'm going to use that OID to filter from here using this @rel ID. So the @rel ID has to equal to the OID coming from PG class. And then I'm going to return this piece of information, the @rel ID, name, type ID, len, @num, and not null. So what can we see here? We see a lot of information. Remember, table foo, when I created it, had only 4 attributes, which are A, B, C, and D. So these are the ones that we created. The other ones up here, those are all like system attributes or system columns. How do you know it's a system column? If you look at the attribute number, the ones that we defined are numbered, 1, 2, 3, 4, and so on. So they start from 1 and they keep going up. The system attributes have negative attribute numbers. So this is something to look out for. I'm not going to get into what these are used for. These have, their own uses. The CTID, actually, this is the one that we may have seen before. This is basically like the row ID of each row. So we've seen that before. This is the type of every attribute. This is actually the type ID. So there's another table that has the type information, and this one is referencing that ID. We'll look at that in a second. And then also we see here, for example, whether any attribute is designated as not null. So the system ones are all not null because these have to be filled out with every row. Attribute A is not null because we define this as the primary key of the table. The other ones are not. And then also it has here the attribute length. So how big is the attribute? So for example, I remember A was an integer, so it has a size of 4 bytes. C was a date, so it's also 4 bytes. D was a double, so it's 8 bytes. And then B was a varchar, so that's like a variable size attribute. That's why it says -1, because each row might have a different value. Now let's look at the types. So as I said, the type information is stored in a different table called PG type. So I'm going to get all the types from that table that have these IDs. So I'm querying PG type where OID equals one of these, the ones that are here. And I'm going to get the OID and the type name. So this will show us the actual names of those types. So we can see that A was type 23, which is int4. B is 1043, which is varchar. C is 1082, which is date, and so on. So we can get the full type information from there. So we've seen three catalog tables. We've seen PG class, PG attribute, and PG type. Again, there's like a lot more than that. We can list all the catalog tables. Since there are tables, they're also stored in PG class. But this is where the namespace comes in. So there's a table called namespace, or PG namespace, that has different namespaces. Let me look at that first. So usually the user tables like foo and so on, these are in the public namespace. And then the catalog information is all in this PG catalog namespace. So if we want to list all the tables in the catalog, what we want is to get all the tables whose namespace is PG catalog. So we can write a query like this, for example. If we select the OID from PG namespace where namespace equals PG catalog, basically this will give us this ID, which is 11. And then we can filter by that in the PG class table. So where rel namespace equals that ID. So this will give us a listing of all the tables that belong in that namespace. So all the catalog tables, basically. So we can see a huge list here of those tables. And yeah, we can take a look at the data in those tables if we want to kind of like, explore a little bit and see what kind of data is stored there. There's a whole lot of them. I'm going to add a link in the description from the Postgres documentation that lists also all the catalog tables, so you can read more about them and see what kind of information is stored in each of those. So yeah, as we have seen, there are many tables in the catalog. We've looked at a few of them, but yeah, there will be many more in the link in the description. So now, yeah, we go back to our diagram. So the analyzer, as we've seen, it looks at the catalog, which is part of the storage, and retrieves the metadata from there to be able to produce that initial query plan and to do the validations on the parse tree. So now that we have that initial plan, the next step is to go through the query optimizer. The query optimizer is often seen as like, the monster in the room. That magic box that takes a plan and produces another plan, and people don't know what happens in there. There's like, some sort of black magic happening in there. Again, I'm not going to get into like the deep details of that today, But on a high level, we can look at the optimizer as performing two functions or two things. The first thing is plan enumeration. So what this means is that it takes that initial plan that we have supplied and it tries to come up with other equivalent plans. So enumerates as many other plans as possible. All of them have to be equivalent to that original one. Things that it may consider would be different operations, may reorder things, may replace an operation with another thing that is equivalent. Things like join ordering, for example, it might switch the join order. It might use different join types like hash join, loop join, and so on. It might push down filters. It might choose different sorting algorithms. It might choose whether or not to use indexes and which indexes to use. So every single thing of those will produce new plans. So let's look at an example. So starting from the plan that we have seen already, that one that has the table scan followed by filter followed by project, let's assume that we have these two indexes. We have an index on the age column and we have an index on the status column. We've talked about indexes before and we've seen how we can use those, right? So one option would be to use the age index, so do an index scan using the condition on the age, which is age greater than 20. So this will give us a bunch of tuples that satisfy this from the index. Then we can apply the second filter on top of that and then do the projection at the end. So that's another alternative plan that is equivalent to the first one. The first one does a full table scan, the second one does an index scan. Another alternative would be to use the other index. We can use the index on the status, for example. Again, the same thing. We do an index scan on that using the condition on the status column. That will give us a bunch of tuples. Then we apply the second filter and then followed by the projection. So again, this is another alternative. A fourth alternative would be, if the system supports it, we could do an index intersection. Again, we've talked about that in the past. So we can do two index scans on the two indexes here and then intersect the row IDs coming from each of them, use these row IDs to actually fetch the corresponding tuples and then do the projection at the end. So every single one of these plans will do the exact same thing at the end. Like it returns the same results, but it does it in a different way. So this is the part of the optimizer that does the plan enumeration. Question on the side, how does the optimizer find out information about indexes, for example, and all these things? Again, this information is available in the catalog and the optimizer has access to the catalog so it can find out what indexes are available, what columns are there, and so on. Once we have all these different plans now, what's next? The next is that the optimizer needs to figure out which one of these is the best. It does that using costing. So it needs to estimate the cost for each of these plans. The optimizer maintains something called a cost model. Cost model means that for each different operation, whether it's a join, it's a scan, full table scan, index scan, projection, a sort, all of these different operations. Each operation has a formula to estimate or compute the cost of that operation. That formula is a function usually of, obviously of the operation itself and also of the number of input rows to that operation. Depending on the number of rows that's coming into the operation, it will produce a cost. So in order to know the number of input rows, again, this is an estimate. So the optimizer needs to know some information about the data. It needs to know how many tuples are there in the table, and then the distribution of some columns and stuff like that. So this is usually maintained as some sort of statistics about the data. These statistics can be regarded as part of the catalog, or it could be stored separately, in a different area of the storage system. All right, let's see what the statistics looks like in Postgres. So these are stored in a different catalog table. This is PG stats. So if we look at the description of that table, basically it's for each attribute. So for each attribute, it stores the schema name, table name, and attribute name, and then it stores some information about that attribute. The null fraction, for example, like the fraction of tuples that have nulls in that attribute, the average width of the data, number of distinct values in that attribute, most common values, most common frequencies, and histogram bounds. Yeah, so a lot of information there. Let's just see a sample of what this might look like. I'll just select, for example, the average width and the histogram bounds for all the attributes in table foo. So this might look a little bit overwhelming. So we have 4 attributes, A, B, C, and D. It might be a little bit difficult to read, but So for attribute A, the average width is 4. Again, it was an integer, so all the values are 4 bytes. And then this is the histogram. The histogram is basically a number of buckets that all have the same, or roughly the same number of rows in each. So basically, it shows here the bucket boundaries. So given those bucket boundaries and given knowing the total number of rows in the table, we can kind of like figure out the distribution of the data. So this is something that the optimizer uses when it's trying to estimate the cost of different operations. So yeah, just kind of like to give an idea of what this might look like. So yeah, so the optimizer uses this statistics to estimate the cardinality or the number of rows as well as the cost for each of the alternative plans. Once that is done, then it can figure out, say, okay, like based on that, out of these n plans, this one is the best. Of course, you may have like a huge number of different plans to look at, right? So each optimizer tries to limit that search space, the number of plans to consider, by looking at only like certain types of transformations, or no optimizer can enumerate every single possible plan. Because that can be almost, I'm not going to say infinite, but like close to that. So optimizers usually have a finite set of plans to work with. Again, this could be like in the thousands or more than that, but it's still finite. And then trying to estimate the cost for each of these can take too long. So again, this is why they try to limit the number of plans that they work with. But eventually they will come up with a plan and say, hey, among the ones that I've considered, this is the best one, and this is the one that you should use to execute the query. Most optimizers or most query engines also provide some way for the user to be able to see what plan it chose in the end, usually using something like explain command or something like that. So let's see what that looks like. All right, let's see what the query plan looks like in Postgres, for example. So to see that, we usually use the explain command with any query that we have. So for example, I have this query here that has a self-join between two instances of table foo. So one of them I'm giving it an alias T1, and the other I'm giving it an alias T2. I'm joining them on column A from each. I have another filter on T2.d, and then I have a order by T2.c, and these are the attributes that I'm returning in the end. So when I add explain before that, then I'm getting the query plan that the optimizer produced, and this is what the plan looks like. So this is basically a tree. Top node, the root node is the sort. Child is a hash node. Child is a hash join, and then the hash join has the two instances of foo, T1 and T2, and T2 has a filter, the one that says d is less than 100. There are tools that kind of like visualize this better. So let's see one of those. Okay, so this is a tool that helps visualize Postgres plans. I will post the link in the description as well in case you want to try it out and play with it. Basically, all you need to do here is paste the output of the explain command and then submit. And it will give you a visualization of the plan in a tree form like this. So this is kind of like the text-based version, kind of like similar to what the explain output shows. And then this is the graphical tree version. And if you hover over each of these nodes, it also highlights the corresponding node on the left side. So you can see here the top node is a sort, below that is a hash join, and then you have the two sequential scans here. This hash operation is actually the building of the hash table. We usually use the right side of the hash join for that, and usually this is the smaller side. And it shows this side as the smaller side because if you remember, our query had a filter on T2, so the number of rows here is actually much reduced. So it uses this side to build the hash table, and then it uses the other side to search into the hash table in order to do the hash join. You could also click on each of these nodes, and it will show you more information about the nodes, and including the number of rows and so on. So yeah, it's a useful tool. Feel free to kind of like give it a try if you want to play with some Postgres plans. There are also other options that you can add to this explain to see more information. For example, you could do explain verbose, and then select. So basically, this will show the same plan, but it will also show some additional information there. For example, this one here, with every node in the plan, it also shows the output columns. For example, it says here the output columns from this node is B, C, and A. So remember, we had A, B, C, and D in the table. We're doing a full scan, but we're not returning all the attributes for only those three because the attribute D is not referenced anywhere. So we only need those three. There is also another piece of information here that says inner unique. So for each join, basically it has an outer side and an inner side, and this one says that the keys coming from the inner side are all unique. So this helps also the optimizer when choosing which plan to produce. So yeah, there's more information that you can get using this verbose option. There is also another option that will allow you to export the explain output in a format like XML or JSON or something to be used for something else later on. So you could do explain format JSON, for example, or format XML. And these are Postgres specific commands. These are not like part of SQL. So each database system may have these slightly different. So if we demonstrate this one, basically instead of this format for the plan, we'll get it in a JSON format that you can parse or do something else with it afterwards. So yeah, just something to keep in mind. All right, so back to our diagram again. So again, we've talked about the query optimizer. We said that the optimizer uses the information coming from the catalog as well as the statistics in order to convert that initial plan to the final execution plan that's going to use to actually run the query. That execution plan, once we have it, that goes into the execution engine. So that is the final part of the pipeline. The execution engine has access to the data, so it uses the data coming from from tables, from indexes, whatever it is, and starts running the operations in the execution plan in the order indicated by the plan, and starts producing the results of the query. So this is basically the pipeline from beginning to end. So yeah, so this is basically what happens to a SQL query from the moment it starts until it reaches the results. Now that we've talked about execution, we can also see some execution information in the output. So instead of just saying explain, we can do explain analyze. So this will still show us the plan, still show us the information that we've seen before, like the estimated cost and all that, but it will also show some execution information. So for each node, we used to see just this part, which would say like the estimated cost, the estimated number of rows, and so on. But now we also have the actual cost and the actual number of rows. So this basically it actually does execute the query, and we'll monitor how many rows are going through each of these operations and how much time it takes, and we'll output that as part of the plan. This helps when you're trying to figure out if your estimates are close to the actual numbers or not, whether your statistics are accurate or not. So you can determine that by looking at the output of explain analyze, which will execute the query and then show you this information side by side. Let's summarize again what we've talked about today. Today we talked about the steps of processing a SQL query, starting with parsing to kind of like convert the query from just a string of text to a bunch of meaningful tokens, to a parse tree, doing all the syntax validations on the way, and then the analyzer, which performs some more validations on that, checking the catalog to check for the existence of tables and columns and so on, as well as types. And it produces the initial query plan. The initial query plan then goes through the optimizer, which uses information coming from the catalog as well as the statistics to be able to enumerate multiple other plans and estimate the cost of these plans and choose the one with the least estimated cost. Then it passes this plan to the execution engine, which then starts executing the operations in this plan on the data and produces the query results. As I've said earlier, there is a lot more detail to each of these components, so we will have more videos to talk about these. Please let me know in the comments which modules are the most interesting ones to you. Which ones would you like us to talk about more? If you have any specific questions, please also add those to the comments. Other than that, yeah, if you like this video, please like and share. Please subscribe to the channel in order to get all the updates. And with that, thank you so much for watching, and I will see you in the next video.